In the previous section, we derived the generic Gaussian probabilistic inference solution, and that was probably fairly intense, and I went through it relatively quickly. What we're going to do now is we're going to take that solution and break it up into smaller pieces, and we still will not get an algorithm out of it in the sense of something that I can just immediately jump to code and write a program for, but we get a sequence of steps that is amenable for creating an algorithm from. So there's going to be two main steps, and each main step is going to have three sub-steps. So overall, we are going to break the solution into 6 steps. So you might want to refer back and forth to the notes in the last section and this section as we go along, especially the summary pane that we had at the bottom of topic 3.5. So every time step, the first thing we do, general step 1A, is to predict what we think the state of the system is right now based on past information. So we are computing an updated prediction of the present value of xk. We are computing x hat k minus. Remember, that's our prediction of the state at time k. The minus says given only past information. By definition, we have said x hat k minus is equal to expected value of the true state, xk, given measurements up to and including time k minus 1 only. And this is where the dynamics of the system get taken into account. We have a state equation, and maybe I should have repeated it, but we have the equation that we know xk equals f of xk minus 1, uk minus 1, wk minus 1. That was our assumed form of a state equation of the model. So expected value of xk is simply the expected value of what xk is, which is a function of xk minus 1, uk minus 1, and wk minus 1. To be able to evaluate general step 1a, we need to know what f is. If f is linear, we can simplify this. If f is nonlinear, we can also talk about how to implement this, but regardless, to go any further, we need to know what f is before we can evaluate general step 1a. So we'll defer that until we talk about linear Kalman filter, extended, and sigma point Kalman filters. Step 1b says that we need to find the covariance of our prediction error. So we would like to find the sigma x tilde comma k minus, that's prediction error covariance, and we compute that just by definition. The auto covariance of x is equal to the expected value of x tilde times x tilde transpose, and we remember that x tilde is equal to x minus x hat. So to go any farther than this, again, we have to know something about the model. It turns out we need to know something about f because we need to know something about x hat. So x hat that was created up here, we have to put into this equation in not the value but rather in an expected sense. And so we need to make some more system level assumptions before we can evaluate this any further. General step 1c says I need to predict the system's output. And this uses prior information. So y hat equals expected value of y given previous measurements. And I suppose I could put a minus sign on there to remind us this is a prediction, but there should be really no ambiguity because if I already had made the measurement at time k, then y hat plus is simply just whatever I measured because I already know it. I don't have to predict it. So the y hat has to be a prediction. And we are aided by knowing that our model is yk equals h of xk, comma uk, comma vk. That was our output equation or measurement equation of our model. So to find the expected value of yk, I substitute in the model equations. Once again, to go any further than this, we would have to know more details about what H is. So we defer that to later sections. The next step is to find the estimator gain matrix. And the estimator gain matrix was defined to be this. It's the cross covariance between X and Y predictions and multiplied by the inverse of the autocovariance of Y. At the moment, we can't go any further than this, but once I know the model of the system, the F and H equations, I can evaluate these, and I can evaluate L. Now I'm ready to compute the output of my Kalman filter. I make the state estimate. This here, I take the prediction from step 1A. I take the output prediction from step 1C. I take the gain matrix from step 2A. I make a measurement at this point of the actual voltage, and I combine all that together, and I get a state estimate of my system. And finally, last step, is I compute the covariance of my estimate. And that we already determined in the previous section. The covariance of the estimate is the covariance of the prediction with a correction factor. I execute all 6 of these steps every time interval, and the output of the estimator is that and that. Both of those things are the output. Everything else is internal to the estimator, and it's used recursively in the calculations. So I have x hat, I've got sigma x. The sigma, the covariance, can tell me about error bounds. So we could say we have high confidence that the truth lies within the estimate plus or minus 3 standard deviations. This is a bit of a short form because we're talking about a matrix here, but what I mean is actually I could probably be precise if I just said x hat k plus or minus 3 times square root of the diagonal of sigma x tilde comma k plus. That's really what I mean. We take the diagonal elements, which are the variances, and we take the square root to get the standard deviations, and we can add and subtract 3 standard deviations. That's one iteration of the filter. We wait until the next sample interval point, we update k, and we proceed. This step 1 ABC, 2 ABC is something that's going to be following us the entire way through this chapter of notes and even into next chapter of notes. It doesn't go away, so let's make sure that we understand what each step is. I've summarized them here. We've got 3 prediction substeps and 3 correction substeps, where in the first 3 substeps I'm predicting the state, I'm predicting the covariance, I'm predicting the measurement. Then I actually make the measurement, and then I compute a gain matrix, I update the state, and I update the state covariance. And I do that over and over and over again. So that's the generic solution broken down into 6 steps that are going to be very helpful ways of helping us to come up with actual algorithms. We'll start with the linear Kalman filter. This is not something that really applies directly to a battery model because a battery is a nonlinear system, but I think it's very valuable still to take this step in the derivation to just help you gain confidence and understanding of how we do things. And we will apply it to a linearized, very simplified battery model to at least get some insight into how it operates. And then we'll proceed to nonlinear systems. In the next section, we're going to take this generic 6-step solution and evaluate each one of the equations for the 6 steps and get an actual set of math equations that we can implement. The assumption is that the dynamics are linear. Linear systems have the very nice property that all of the PDFs are in fact Gaussian if the inputs are Gaussian. So the assumptions that we made in deriving the filter steps hold exactly, and the Kalman filter is in fact the optimum solution to a state estimator. The linear form means this. It means that my model, it looks like xk is some A matrix, which may be time varying, so that's why it has a time subscript. So an A matrix times the previous state plus some possibly time varying B matrix times the previous input plus a process noise. And the output that we measure, y, is some matrix times the state plus some matrix times the input plus some measurement noise. This is not too different from our battery model, and our battery model is fairly linear, but it is not exactly linear, so we're going to do actually quite a bit better with nonlinear Kalman filters later on. We assume that the noises are mutually uncorrelated, so W is not correlated with V and vice versa. They're white noises, as we've talked about. They're Gaussian random processes. They've got zero mean, and they've got covariance matrices, which really talks about the size of the disturbance, how powerful the disturbance is, and these covariance matrices have known value. So what that means is the expected value of the process noise at time n times process noise at time k transpose is going to be equal to a constant matrix sigma w when n equals k, and it's 0 when n is not equal to k because of the whiteness criteria. Similarly, for sensor noise, expected value v at time n times v at time k is going to be sigma v tilde at time n equals k, and at 0 otherwise. And furthermore, we're going to assume that the expected value of wk, and this would be greater than equal to 0, wk and the initial state is 0. So the process noise in the future is not correlated with the state of the system at any point in time, like 0. Is what that means. And so it says that the state does not cause or influence the process noise. It's the other way around, is what this assumption is saying. So the assumptions on these noise processes W and V, the linearity of the system dynamics, are really never met in practice. Linearity is a nice idea, and systems can be very close to linear, but they're never exactly linear. The consensus is, though, that this really works. Kalman filters really do work, even when the system is a little bit nonlinear, even when the noises are not exactly Gaussian and so forth. Kalman filters come up with estimates that are reliable and that can be used inside of other applications, such as we shall be doing. So that brings to an end our background on probability theory, our introduction to sequential probabilistic inference. Now, at last, we are able to derive the linear Kalman filter steps, which we will do next, and do some examples, and I hope you will begin to gain insight into why the equations that we get actually make sense, and how the filter works, and how you would implement it in practice, and so forth.